Back in 2019, the National Security Agency publicly released their internal tool for analyzing compiled code. It used to be for the eyes only, but now it's free under the Apache license. And since it went open source, the community has added a ton of features. But how can we actually use it? Usually Ghidra is the tool for dissecting malware to figure out how an attack happened, or for some reverse engineering just like the guys from Dragon Sector. They use tools like this to expose some nasty tricks hidden inside the never changed software, and they paid a lot for this. And if you work with embedded devices, you know the drill. If your compiled code gets exposed, your friends far away from Asia might just clone your entire product overnight. To decompile the bin file, in this mini-series I will show you how to take a compiled binary, inject your own code and actually run it on STM32. Starting from the beginning, I will be using STM32 CubeMX, which is the software to generate the code for our microcontroller. I will not be getting into the details how to configure the software itself, but I want to show how I configure the microcontroller. It's the default setting of the interrupts and the clock. I only changed here the output of one of the pins, which is configured as the LED. I named it LED, which we will be using later in the example. Here's the clock configuration. Nothing changed here. Default settings 8 MHz, and as the project manager, I changed it to STM32 Cube IDE and named it the Ghidra example. Here's the code generated by the CubeMX software. I modified a bit the while loop and added one function actually. Basically this while loop is now toggling the LED pin every 500 milliseconds, and every fifth iteration it executes the function called send word data. However, we are not sending any word data, it's just dummy function with some basic mathematical operation, and I called it this way just for the example purposes, and it's not empty just because there is optimization of the code, and I wanted to make sure that the compiler includes this code inside the bin file. Let's move on to Ghidra. We start by importing our bin file into the project. The first step is to select the correct processor language. Since we are dealing with Cortex-M3 microcontroller, we select that architecture with little endian byte order. Now let's configure the memory, and before we type in the address, let's take a brief detour to explain the memory layout. Ghidra needs a book to know what each address represents. If you look at the memory map in STM datasheet, you will see that the physical flash memory, where our binary actually resides, starts at this address. So this is the base address we need to set for a file during import. However, when the core boots up, it looks for the vector table at this address. This is known as the aliased memory region. Depending on the boot mode configuration, the hardware redirects any reads from address 0 to any different physical location. It could be a system memory for the bootloader or main flash memory. And since our code runs from flash, address 0 is effectively a mirror of this address. To represent this in Ghidra, we will create two memory blocks, the main block at this address containing the data, and a mirror block at the 0 address to handle the initial vectors correctly. Let's set the flash memory address and open the Ghidra code browser. Before we let Ghidra analyze the file, let's open the memory map window. Here I'm adding an additional block starting at address 0 with the same length as our bin file. This acts as our mirror. There is one more crucial step before we start the compiling. We're going to use SVD-Loader to make our lives much easier. You can find the link to the SVD-Loader script in the description below. SVD stands for the System View Description, and it contains details of the memory map peripherals and registers of the microcontroller. It is useful during the analysis because we will not have to read hex addresses, and Ghidra will map the hex addresses to the logical names of the peripherals or registers, which makes the code much more user-friendly. I've downloaded the SVD file for this specific microcontroller from the GitHub, and again, link is in the description. Now that the logical names are imported, all the peripheral addresses are mapped to their readable names. With that setup complete, we can finally run the auto-analysis. Ghidra will start processing the file, and after a moment we will see the decompiled results. At the very beginning of the file, we see the decoded vector table. In ARM architecture, the first 4 bytes correspond to the stack pointer. The second entry is the reset vector. This is where the code execution begins. Thanks to our memory mirror, Ghidra correctly identifies this. Following this address takes us to the reset handler. We can see some basic initialization loops and function calls here. After the reset handling is done, the code should jump into the main loop of the program. So if we look at the last function call in this handler, we should find something familiar. In the original C code, we had 3 specific actions and we can see them reflected here in Ghidra. We have a function call with 2 arguments, another function call without arguments, and last one function call with 1 argument. And all of this in the while loop. This confirms that Ghidra has correctly decompiled our firmware, or at least this part. Let's look at one more technical aspect. If we examine the assembly code, notice this LDR instruction loading a value into register from a nearby memory location. This technique is called a literal pull. The compiler places a constant at the end of the function because they are too large to fit directly inside instruction. Notice that the value stored at this address is automatically identified as GPOC. This is the power of the SVD-Loader we ran earlier. Without it, this would just be a raw number. So where does this leave us? We have cracked open the black box. With the SVD loaded and the code decompiled, we can do much more than just read. Now, we can alter the device reality. Instead of blindly fuzzing the file, we can now target specific instructions. If you want to make the LED blink twice as fast, it's now easy. If you want to remove a delay entirely, done. But the real magic happens in the next episode. I will show you how to hijack the processor to run our own code, crafting new features onto the existing firmware without adding a single byte to the file size. It's going to be a deep dive into binary patching, so make sure you are subscribed, and if you like this video, press like button below.